And here is one idea, and the idea is, instead of looking at x, maybe I'll put it here, instead of looking at the particular state and particular time, look at distribution of states. This is the duality that you use a lot because that's the essence of almost any transform that you learn, certainly Fourier transforms, but so they're dual pictures. There's a local way of thinking, there is a global way of thinking. And in dynamics, local way of thinking is good for short times. You know, you can predict very accurately 3 steps of a robot or something. And global is when that thing fails. So that's what I want to do. And the reason why I taught you all this local stuff and reviewed it is because there is a beautiful set of dualities that tell you how to do a local computation and give a global answer from it. And I gave you the first example, which you don't seem to be very impressed by, but I gave you an example that in this world you can compute. I did it only for topology, so for a case where you only count ways of doing stuff. You can compute all prime orbits, you can compute all their repeats, if you have prime orbit repeat follows. And then this was obtained by taking a trace of the matrix, so every periodic point contributed. So there was a count of how many periodic orbits belong to the orbit. They contribute all in the same way because it doesn't matter where you're on periodic orbit in time and you come back. So you get your and one. And then there was a weight associated with the orbit which I call little prime. So that's something you compute exactly. You go someplace, you find a very special point that does this, you find a very special point that does this, and you try to do it intelligently and systematically, the right-hand side. On the left-hand side, there is an operator, and it has eigenvalues. So on the left-hand side, you find out that you're looking at a sum that looks like. And what we found on example of topological entropy of counting, that the only thing we need to know is the spectrum of the law that we have, and law is linear, it's a transition matrix. So that's why we care about left-hand side. We want to predict the growth rate, for example, how many orbits there will be, as a simplest example. But this will be a totally general way of computing any average that can be done in time. So this is global, and this is local. And it's totally amazing. And if you don't understand it on a 2x2 matrix or 3x3 matrix, you know, then we're in trouble. But that's the idea. So something has happened. First time in the course, there's an idea. And I don't know who to give a credit for idea. These kind of things go all the way back to Gauss and Euler, etc. People who learn something about statistical mechanics know about Liouville and phase space, and yeah, so it's in that general thing. But the modern idea is only from 1970, roughly. It's only become a subject rather recently. So this is the great thing. And as all things that are easy to understand, it turns out this is easy to understand, but this is not the reasonable way to compute eigenvalues. They just relate some of our eigenvalues to eigenvalues, and you can do something, but it's not a really bright thing. And something looks wrong about this formula. You will correct me. What's wrong about this formula? You want these on the right side? Yeah, so, you know, that's a matter of definition, but here I decided to give a weight. This is an arbitrary real number, actually could be complex, which only keeps track of the length of the periodic orbit. We're just counting how many orbits of given length. So you're happy on the left side. So So this is now the idea, and it's extremely easy to understand it in this form. The only reason you don't understand why am I making you write it in this form, but you have no problem with computing matrices, multiplying them, taking traces. That's the right-hand side. And on the left-hand side, you know that matrix has eigenvalues. Somehow, conceptually, it shouldn't be hard. Now, what's wrong about this, or what's disappointing about this formula, is that we pretend that everything is equally important. So as we explore the state space, which you partition in little neighborhoods, this formula seems to say it doesn't matter where I go, it's all the same. And that's not how the physics will work. The physics, or sophisticated mathematics, will give different weights to different paths. And here the idea, I think, comes from Kolmogorov. So, Kolmogorov was the first one, I think, to start really thinking, how would I think of entropy of dynamical system? But this version is not Kolmogorov versions, but conceptually it came from there. So I did this not because I care about counting paths. I mean, it's actually important because when you do a calculation, you need to know how many terms you have to include. So if you can't count them, you're really screwed. So in practice, it's important to do this because that's a check on whether you have found all the periodic orbits you need to produce an accurate result. But it's not terribly interesting.